Today we're going to learn about how to create a line of fit through a data set. First of all, we've got a definition of what the line of best fit is, which we'll learn how to calculate with our graphing calculator tomorrow. However, today we're going to just learn how to kind of eyeball a good line of fit through a data set. You can see here the steps to creating a line of fit through a data set. You want to calculate the mean of the x values and the mean of the y values. That becomes a coordinate that you plot on your scatter plot, and your line of fit should go through that data value. And you should try and balance it through the rest of the data points so that you have roughly the same number above and below the line. But you also want to consider spacing as well. If the ones above the line are really close and the ones below are further away, then you may not have the same number. You want to kind of look at the spacing as well. So here we have an example. This is from our opening problem, which we've seen before. It is the discus throw. So the age of the person and how far they throw the discus, we have already determined that they are positively correlated, and that it seems to be a fairly linear correlation. So now we have calculated the mean age is 15 and the mean distance thrown is 29. So we're going to plot that point on the graph, and then we're going to sketch a line of fit through that point that again balances the number of data values above and below, as well as the spacing. So as you can see, we have about 7 data values above and only about 5 below. However, when you look, the data values that are above the line are a lot closer than the ones that are below. So I'm trying to balance the spacing as well as the number of data values. There are 2 ways that we can use our line of fit. One is called interpolation, which is when we use our line of fit to estimate a value between the known data values. And then there's extrapolation when we look beyond what is known. So if you look at this graph here, you'll see we've got what's called a lower pole, which is the smallest data value, the smallest x value, data value, and then the upper pole, which is the largest x value, data value. Anything between those 2 x values is interpolation. Anything smaller or larger would be extrapolation. So we've got a note of caution here. When you extrapolate using a line of fit, it's not always the best estimate, because what happens beyond the known data may no longer be linear. So here we've got a couple of examples, one of interpolation. So if we use a data value of 14, that is within the known data values, so it's a fairly accurate prediction of what a 14-year-old could probably do with the discus. And then we predicted what a 30-year-old might be able to do, which is beyond the data. So it's an estimate. It may not be very accurate because the data will likely no longer be linear beyond a certain point, because humans just can't continue to throw further and further just because they get older. All right, we'll take a look at one example together. We have on a hot day, cars were left out in the sun, and so we are going to be plotting the time they were left in the sun versus the interior temperature of the car. In order to get a good line of fit, we need to know what the mean of each data set is. So I have calculated those averages for you. The average time that a car was left in the sun was 30 minutes, and the average temperature was 38 degrees Celsius. So we're going to plot that point on the scatter plot, which I already have set up for you to save us some time. And then we'll place our line of fit through that point. I have 3 data values above the line and 3 data values below the line. They look fairly evenly balanced, so we're going to call this our line of fit. We're going to answer a couple of questions on this line of fit. The first one is to predict the temperature when the car was left in the sun for 35 minutes. We will be using our line, not any of the data values. So when we go back to our graph, on the x-axis we've got our time. We'll go over to 35 minutes on the x-axis, and we'll read that temperature off the y-axis, and it looks like it's roughly 40 degrees Celsius. And then we're asked to estimate what the temperature would be if the car was left in the sun for 75 minutes. Since on this one our graph doesn't extend to 75 minutes, what we can do is use the slope and the y-intercept to get an equation and use the equation to predict the temperature. Our y-intercept looks like it's roughly 28.5. And for our slope, we just want to find any two nice coordinates on our line. We know that the mean is on our line, so we can use that coordinate. And then it looks like the graph goes through this coordinate as well. Notice that the rise is by 1 when we're going up, so we can count these by 1s. So that's a change of 6 degrees in the temperature. But when we're counting our run, we need to make sure that we're using the scale at the bottom. That's going from 12.5 to 30, so that would be a change of 17.5. Our slope is change in y over change in x, or roughly 0.343. Our y-intercept was 28.5, which makes the equation of our line 0.343x plus 28.5. Subbing in the minutes for x, replacing x with the 75 minutes. And then solving to get our approximate temperature. Rounding to the nearest whole degree, we get 54 degrees Celsius. Finally, we're asked to comment on the reliability of our predictions. 35 minutes was an interpolation, so it should be fairly accurate. "75 minutes was extrapolation. The data may no longer be linear. So it's not reliable." All right, so now you have an assignment on this material. Work together in your groups to understand it as best you can, and I will answer questions for you tomorrow.